Okay, today's video is going to be about TMDLs and pollutant loadings, specifically the calculations that are used to ensure that the impaired waters, TMDL, 303D, or others, that you're not seeing an increase in the pollutant of concern. Specifically in South Carolina, a majority or a large portion of the state is under a fecal coliform or E. coli, a bacteria, TMDL, or 303D impairment. There are several other impairments, whether it be turbidity, phosphorus, bio, but definitely fecal coliform is the one that you see the most in South Carolina. So we'll take a quick look at the permit requirements specifically for South Carolina by DHEC. Other states have similar language and requirements though. Now we're looking at page 52 of the Construction General Permit, section B here. And if you haven't read this section, if you're not familiar with this section, look at bullet point number 2 that I'll highlight. So for construction sites that disturb 25 acres or more and which have stormwater discharges draining directly to an impaired water body, I'm going to stop here. This, if you read above, it says it's just for 303D impairments, but the MS4 permit actually specifies that it's for TMDL waters as well. But it says the SWIP must contain a written quantitative and qualitative assessment. So quantitative is a measurable assessment that has to use calculations. All right, so how do we do that? Well, there's two methods that we're going to discuss today. There are other methods. The first is the use of the ideal model. And the ideal model is a really powerful, really neat water quality and pollutant loading stormwater modeling program. I was actually employed by the company that developed the ideal model for 8 years and was involved in a lot of the beta testing. And it was ahead of its time when it came out, and really based on the regulations, it's still ahead of its time. Especially in some areas, but it is a very powerful, very neat tool and program for accurately estimating pollutant loads from a wide range of pollutants that are in stormwater. The other method we're going to discuss is something called the simple method, and like the title states, it is very simple, just a formula that you plug in, and then you essentially do a reduction based on the BMPs at the site, based on literature and data for the removal percentages of those BMPs. During my discussions with DHEC, specifically Jill Stewart, I believe, she said the simple model is an allowable method to do the quantitative analysis. Obviously, ideal model will give you better results, more accurate results. But both are acceptable methods per the state. Okay, so the first method we're going to look at is the ideal model. And similar to other programs, you'll see a schematic that describes the watersheds. And just like with your hydrologic and hydraulic analysis, you'll have a pre-development conditions, and you'll get a pollutant loading pre-development. And then you'll have post-development conditions, and you'll get a pollutant loading in the post-development conditions. The watersheds should pretty much match what you see on your watershed maps for your hydrology calculations. One thing that Ideal does a little differently is they break it up for each watershed in the pervious area inputs and the impervious area inputs, and that's done to determine the pollutant loadings. So that's one thing to be aware of, that you have for each watershed, you're going to have impervious area inputs and pervious area inputs for area, for curve number, and everything else. Now, if the watershed is 100% impervious or 100% pervious, Ideal gives you an option to put in, where you don't have to do the separate inputs. But most watersheds by nature include pervious and impervious areas, so that you'll most commonly see them broken out. So when you're reviewing areas, reviewing curve numbers, you'll want to have that in mind and know that, during your hydrology calculations, watershed A may be 20 acres, but when you come to ideal, watershed A may have 10 impervious and 10 impervious. So the first things you'll see in ideal are these inputs. Just like any model, you'll have your area, curve numbers, and things of that nature. So you'll want to, just like you do with your hydrology calculations, you'll want to make sure the areas match the watershed maps. You'll want to make sure the curve numbers are appropriate. But now the most important thing, in my opinion, when reviewing the ideal calculations is making sure the correct EMC data is put in. In the model, you don't get to see this when you're reviewing the output, but in the model they'll select the land use or land cover, and ideal will automatically generate the EMC. And an EMC is an event mean concentration. It's just a loading for a specific pollutant based on the watershed use. So in ideal, right below the watershed inputs, you'll have the pollutant inputs. So as you see, where my hand is here, nutrient inputs, bacteria inputs, and as you can see, they have EMCs for the different pollutants. Since bacteria is the most common one, we'll look at it. Right here where my hand is, there's an EMC of 25,800 CFUs per 100 milliliter. So you'll want to check to make sure these are representative of the watersheds. So one way to do that is Greenville County Stormwater Manual, and I believe this is in Chapter 9. You can see the tables 9.3, 9.4, 9.5. And you can locate this document by going to Google, typing in Greenville County Stormwater Management Design Manual. You can go to their website, their land development website, and it's on there. Pretty easy to find. If you have any problems finding it, just give me an email and I'll send you a link to it. But in that table, they provide the different EMCs, and you'll want to make sure that the ones that are used are representative of your site that you're reviewing. Very useful table here. And this isn't the only source for EMC data. You can find others online. Now, if you're in the South Carolina, North Carolina area, I would recommend using these unless your municipality has adopted a certain reference for these. Now, for reviewing the actual loading, like I said, you'll want to check each watershed to make sure the EMC data, the watershed area, curve numbers, and that type of thing are accurate. But for checking the pollutant loading from the entire site, you'll see they have an outlet here, and Ideal makes you tie everything to an outlet. You can have ponds and vegetative filter strips and other treatment devices in between, but everything will eventually go to an outlet. And you may have multiple outlets, so you'll have to sum those up, and Ideal will actually do that for you. But remember, when you're checking the pollutant loading, whether pre-development or post-development, go to these outlets, to the inputs or to the model results for these outlets. And now we'll scroll down. I'll slowly scroll through the model, just looking at all the different outputs. So this is just watershed inputs. And don't get confused by this annual loading results. That's not what you're checking. I'll show you what you want to check here in just a second. And you'll have the non-routed connectors, which is just tying watersheds to ponds and watersheds to outlets and that type of thing inside the model. But don't get confused on looking at those. And just more watershed inputs. So scrolling quickly now, let me go a little faster here to get to the bottom. Once you get to the end, here we go, you'll have the outlet. See where my hand is, outlet. And this is where you're going to check your pollutant loadings. So for this specific site, if we're looking at bacteria, I believe it's going to be on the next page. Yes, here we go. Bacteria is actually at the very bottom. you're going to be looking at the total bacteria discharge. So this number right here where my hand is, if you can see right here. Total bacteria discharge. That's your pre-development loading for this specific site. So jot that number down. Then you'll navigate to your post-development calculations in IDEAL. And as you can see, more complex here in the schematic. They have ponds, filter strips, that multiple watersheds. Just like with pre-development, you'll want to review that the EMC data, the curve numbers, areas, all align like they should. But again, you see how everything's tied to an outlet here. So you'll want to look for this outlet number 7. There could be multiple outlets. Get the one at the very bottom of the site. Okay, now I've scrolled down to the bottom and found outlet number 7. And just like with pre-development, there's a total bacteria discharged here where the cursor hand is circling. And you'll go over in 3.1 times 10 to the 12th column. That's the total amount discharged throughout the year. And backing up here a little bit, IDEAL does not look at a single storm. It can, but what it typically does for these pollutant loadings is it does a annual probability distribution of storms. So it looks at a 1-inch storm, a half-inch storm, multiple storms that you would see throughout the year, based on the geographic area. And then gives you a loading based on the typical rainfall that you would see throughout the year. So my two big key takeaways from IDEAL are: go to the outlets to find your pollutant loading discharges at the very bottom of the schematic. You can look at the schematic and see where you need to go in the model results. And then also keep in mind that for each watershed you will typically have pervious area inputs and impervious area inputs. So it breaks each watershed into two kind of sub-watersheds, impervious area and pervious areas. Okay, so now we're going to look at the simple method. And to find the reference for this, I'll show you. Just go to Google, type in SCDHEC simple method, and stormwater should give you the results you need. There you go, it's the top link. Okay, so this is a link from DHEC's website, and it uses this formula to calculate a loading for your site. So this first equation is for phosphorus, nitrogen, those type of nutrient pollutants, and the bottom equation is for bacteria. So use these to determine your loading. So in these equations, L is obviously the annual load of the pollutant, whether you're looking at the bacteria or the nutrient equation. R is the runoff in inches, the annual runoff in inches, so that's going to stay the same pre-development or post-development. The area should stay the same pre-development, post-development. And then you have these conversion factors. The only input that changes is this C, the pollutant concentration. So you will use the table A2 in this document to get your C factor, or your pollutant loading concentration factor. That goes into that formula. And then you'll do one equation for pre-development, one equation for post-development using different C factors, get your results for your loading, and then you can account for the removal percentages of the BMP. So there's another table in this document, table A4, that gives you some suggested removal rates for different BMPs. You have wet ponds, wetlands, filtering practices, infiltration, water quality swells. And it has different removal percentages for different pollutants. Now, if you don't see your specific BMP or you don't see your specific pollutant, you can use other sources for these removal rates. I know in DHEC's BMP manual they reference some removal rates for some BMPs, and you can find other sources online. And then finally, you use this equation that just gives your pollutant load in pounds, your annual load, and then multiplied by your efficiency. So I mean, very simple equation there. Just reduce it by the removal percentage amount. I guess that's all for this video. If you have any questions, please email me, call me anytime. Thanks.